I called this method 1 for solids of revolution, which is called the method of disks. And now I need to tell you about the other standard method, which is called the method of shells. All right. So this is our second method. I'm going to illustrate this one with a holiday-themed example here. This is supposed to be a witch's cauldron. Whoops. Which witches? Well, maybe more than one witch will have this cauldron here. All right, so here's this shape, and we're going to figure out how much liquid is in here. I'm going to plot this. Maybe I'll put this down just a bit lower here. And I'm going to make it a parabola. This is y equals x squared. And I'm going to make the top height be y equals a. All right, so here's my situation. And I want to figure out how much liquid is in here. Now, the reason why I presented the problem in this form, of course, is really to get you used to these things. And the first new thing that I want you to get used to is the idea that now we can also revolve around the y-axis, not just the x-axis. So this one is going to be revolved around the y-axis. And that's what happens. If you spin the parabola around, you get this kind of shape, this kind of solid shape here. All right? Now, I'm going to use the same kind of slicing that I did before, but it's going to look totally different. Namely, I'll draw it as in red again. I'm going to take a little slice over here, and now I want to imagine what happens if it gets revolved around the y-axis. This time, it's not a disk. Actually, if I revolved this around the other way, it would have had a hole in it, which is also possible to do. That's practically the same as the method of disks. You'll maybe discuss that in recitation. Anyway, we're going to revolve it around this way. So again, I need to sweep it around, swing it around like this. And I'll draw the shape. It's going to sweep around in a circle, and maybe it'll have a little bit of thickness to it. And this is the thing that people call a shell. Right, this is the shell, so-called shell of the method. I would maybe call it a cylinder, and another way of thinking about it is that you can maybe wrap up a piece of paper, and right, like this. There it is. There's a cylinder you can see. Very thin, right? Very thin. All right. Now, the reason why I used the piece of paper as an example of this is that I'm going to have to figure out the volume of this thing. Its thickness, as usual, is equal to dx. Its height is what? Well, actually, I have to use the diagram to see that. The top value is A, and the bottom value is what we call Y. So the height is equal to, A minus Y. Now again, this is an incredibly risky thing here, and I've done this before. I pointed this out on the very first day of lecture. The letter y represents a lot of different things. And in disguise, when I call this y, I mean y is equal to x squared. In other words, the interesting curve. I don't mean y equals a, which is the other part. In general, you might think of it as being equal to y top minus y bottom. So there are, of course, two y's involved in disguise. But we have a shorthand, and the sort of uninteresting one we call by its, we just evaluate immediately, and the interesting one we leave as the symbol y. All right?